All right. So we've talked about degrees of freedom, right? Which is really trivial for us to start this course. So now let's go into the next step, which is the Newtonian approach, right? So Newton laws we're very familiar with, right? I mean, they've been, being into our heads. So we're going to talk about Newton, and then we're going to talk about the Lagrange equations, and then the Euler equations. Let's start with Newton, right? We already know Newton's law, which is F equal to ma, right? You can generalize that law as saying, okay, the sum of forces is equal to the sum of, masses and accelerations combined, like the combined mass and the combined accelerations. Okay, so that being said, you can describe that any particle, right, or body that's undergoing dynamics exhibits some form of that law, right? Because you're actually moving that body. Okay, so this is where our equations of motions come from, because you can, another way to write that law is to come and say, okay, my f vector is equal to the m times the a vector, right? So in other words, I know I keep like trolling this, but sigma fx, sigma fy, sigma, there is a bad sigma. All right, sigma of z is equal to the mass, assuming that nothing's changing there, and then the resultant acceleration in dx, acceleration in ey, and acceleration in dz. Okay. All right. So I guess when we talk about Newton law, right, we need to define a concept here that is very important, which is free body diagram. I'm sure many people are familiar with it, but since it is very important, I'm going to go over it here real quick. So free body diagram, meaning that I take that part. So I'm going to give an example here. I have, some ramp with some theta. I have some mass sitting on it, right? And that mass, let's just say it's moving somehow. To excite this, I am. Let's just leave it as this. So I have something like this, okay? So if I want to do a free body diagram of this, I'm just gonna segregate the mass. So I'm gonna say, okay, here's my mass, right? I have mg acting this way. I have gravity acting this way, and then I have, in accordance with that axis, right, I have a theta here, right? And then that mass is exhibiting or is feeling some normal force, right? And then is being acted on with some friction force, right? So this is my definition, or this is the definition of a free body diagram. You're taking that body out there and you're treating it as a particle, right? And you are analyzing all the forces that's happening on it. So from here I can start writing some equation of x, equation of y, equation of z, and all of those, right, is going to equal to my acceleration vector. Like acceleration mass times acceleration vector. Okay? All right, well, let's go into an example. All right, so we have some system here. So the first thing I want to talk about is how many equations of motions do I need. So equations of motions is going to equal to your degrees of freedom in the system. So in this case, I look at the system and I say, okay, so I have 6 times rigid bodies. I don't have any rigid bodies. Planar bodies. So 3 times planar bodies. I have 1 planar body. Okay, constraints, minus constraints. So do I have any constraints? Well, it looks like I have a constraint in this direction, right? And it looks like I have a constraint on the rotation. So it's going to be minus 2 constraints. So that being said, I'm going to get that this is a 1 degree of freedom system. Okay, so to excite things a bit, let's put some f of t over here. Okay, so forcing function. You can, if you don't want to put a forcing function, don't put a forcing function. It's just equated to 0 in the end. It's very simple. So in this way, I know it's a 1 degree of freedom system. So let's try to get our equation of motion. So we say sigma of f, you know, in the x direction, and this being my x direction over here, and this being my x dot direction over here, and you know, x double dot direction, etc. Okay, so I'm gonna say, let's see what my forces are. When you do the equations of motions, it's very important that you stay consistent with your signing. So usually what I do is that if I have an arrow pointing somewhere, I'm going to stick with that as a positive and everything else is negative. Okay, so in this case, I will say, okay, so f of t is positive, and I'm going to say minus k1 times x. How did I know that? I'm sorry I did it in my head, but the first thing we do is you go to a free body diagram, right? And the free body diagram is going to tell you, okay, I have some f of t here, and then I have some f of k here, and then I have some f of c here, and then I have some, you know, mg, and then I have some normal force. Now, since I'm not interested in this direction, I'm only taking the stuff in this direction, so I'm going to say, okay, I'm going to say that, let me take this out here. So I'm going to say that f of t is going to be a minus f of k minus f of c is equal to, you know, the sigma f, so there's no sigma f of x. So that being said, I'm going to come and say, okay, ma, or as I like to call it, x double dot, right, because we're going in that direction, that's what a is going to equal to f of t minus f of k is equal to k times the displacement, which is x, and then f of c, which is going to be c1, right, it's k1, c1 x dot. So that being said, my equation of motion is going to be, if I were to put the terms on ends together, m x double dot plus c1 x dot plus k1 x equal to f of t. So this is here my typical 1 degree of freedom equation of motion for a system like this. Okay, well, let's complicate this a little bit. Let's say I have 2. All right, so how many degrees of freedom do I need? Well, right away, how many rigid bodies? 0. How many planar bodies? Okay, well, I have 2 planar bodies. All right, how many constraints? Well, they can't move up and down, and they can't rotate. So I have 4 constraints, because there are 2 constraints per each body, so that's 4. So that means I have a 2 degree of freedom system. Okay, well, let's write the equations. Well, let's take mass 1. So I'm going to take my free body diagrams over here, and I'm going to say, okay, let's look at mass 1. Well, mass 1 is exhibiting gravity, mg, and a normal force, which they're canceling each other out because they're restrained, right? And then I have some fk1, and then I have fc1, and then here I have some fk2 and fc2. Okay, again, I'm assuming my motion over here is going to be x1, and my motion over here is going to be x2. So that's my axes. Okay, well, let's write the first equation of motion. So f of x1. All right, well, let's see. What is in the direction? In the direction I have k2, right? And this is going to be a displacement difference between both. So the displacement here, if I'm looking at it from x1, which that's what I'm going to stay consistent as, I'm going to say x1 minus x2. Okay? All right. And then I go next, as I have some friction force or damping force, and I'm going to say this is going to be equal to C2, again, same situation, x1 dot minus x2 dot. Okay, and I am going in the other direction now. So it's like, okay, I have my k1 times x1, and then I have minus my c1 times x1 dot. And this here is going to equal to my ma, or my mx double dot, so x1 double dot. So this is my first equation of motion. So this here is my number one. Okay, that's my number two equation of motion, because we said we need two. All right, well, my number two equation of motion is going to equal to my second free body diagram. So let's say this is free body diagram 1, this is free body diagram 2. So you're going to need, one for each body, hence free body diagram. So that's how many number of free body diagrams you're going to have. All right, let's make this exciting, and let's put some forcing function f of t. All right, so I have some forcing function f of t. I have gravity down, mg. I have my normal up, don't use it, don't care. I have my tension acting in the other direction, and I have my friction or dampening acting in the other direction. Make sure you are consistent with the way you write those in terms of direction and the same definition. Okay, so that means that my fx of 2, right, is going to equal to the forcing function minus the first spring-related force, which is minus k2 x1 minus x2. Where did I get that? That's the same term over here, just in the negative. And my friction slash damping force, which is x1 dot minus x2 dot. Again, same as here, just in the negative direction. And this is going to equal to mx2 double dot. So this is my second equation of motion. So it's very easy, very trivial to get equations of motions based on whatever systems you have, very systematic. So if I were to say, all right, well, how do I go about this? Well, in order to go about equations of motions, you're gonna have to, number one, determine degrees of freedom, right? Find out your degrees of freedom. Number two, free body diagram each system. Okay. Number three, write all applicable equations of motion for each system. Okay. There is one that I left here, but I'm assuming it's going to be put into your free body diagram, which is define your coordinates. Define coordinates. That is very important. Okay, awesome. Thank you. Well, I hope that was good. See you next video.